Hello everyone. We're going to look at solving a system of differential equations using Laplace transforms. But before we do, we have to review Kramer's rule for solving a system of two equations in two unknowns. So here's a general system where A, B, C, D, E, F are assumed to be constants. Basically what we do is we calculate, I'm going to call it D for denominator, and when it's set up in this form where the x's and the y's or the unknowns are on one side and constants on the right side, then you just peel off the coefficients of the variables, and so A, C, B, and D, and set up a 2 by 2 determinant, and then you can calculate that. Of course, it'll just be simply AD minus CB or BC, whatever you like. And then you calculate the numerator of x. So I'm going to denote it by n sub x. And that's done by setting up a 2 by 2 by determinant again. But now, whatever variable we're looking for, in this case the x variable, we're going to replace that column by the solutions. So E and F take up the x column, and then we leave the y column as B and D. And then we calculate that, ED or DE minus FB or BF. And similarly, we'll do the same thing for the y's. I'll call it n sub y, for numerator of y. You leave x alone now, and you replace y by the solutions. And then, of course, you calculate that determinant. So AF minus CE. And then the solutions to the system are that x is equal to n sub x over d, and y is equal to n sub y over d. So that's just showing it in general. So as a specific example, we'll calculate the denominator first, which again, it's in standard form here. Peel off the coefficients of the x, 5 and 2, coefficients of the y, 7, negative 4. Calculate the determinant, we get negative 20 minus 14, or negative 34. And then for n sub x, it's going to be replace the x's by the solutions, 13, 12, and leave the y's, 7, negative 4. Calculate that determinant, and that's negative 52 minus 84, which gives us minus 136. Okay, and if we want the solution for x right away, that means that x is going to be, again, n sub x over d, so negative 136 over negative 34, and that goes in neatly 4 times. And then we'll do this for y as well. Now we leave the x's alone, and we replace the y's by the solutions, and calculate the determinant. We get 60 minus 26, which is 34. And now the solution for y then is n sub y over d, which would be 34 over negative 34, or negative 1. Okay, so that's how easy it is to use Kramer's rule, and definitely necessary, as we'll see. Here's a little procedure if you like to solve the differential equation. We're just simply going to take the Laplace of both sides of both of the equations, algebraically manipulate to obtain the Kramer's rule form. So we're going to end up with x of s and y sub s, y of s and x of s, and they're going to be like the x's and the y's. Then we'll use Kramer's rule to solve for them, and then take the inverse Laplace to find the functions that are the solutions to the differential equations x of t and y of t respectively. Okay, so an example. Here's the system. Let's remind ourselves of the basic transformations for the functions. That is the Laplace of, I want to make my lowercase x kind of cursive like we did last time. Laplace of x of t is x of s, and the Laplace of y of t would be y of s, and then the Laplace of their derivatives, x prime of t, is going to be s uppercase x of s minus x of 0, and then the Laplace of y prime of t would be s times y of s minus y of 0. Okay, and we're only going to be looking at first order, so we won't need the second derivatives. So obviously those things you want to make sure you understand and write down on your cheat sheet for the final exam or fifth exam here. And I'm just trying to focus a little bit. Okay. And so we'll start by taking the Laplace transform of each of these two equations. You can see the initial conditions here. And I'll try to group them in two lines as we go. As you'll see, first off, the Laplace of x prime of t. So remember, just like before, use the linearity property and express the functions as in functional notation as functions of t. So Laplace of x prime of t will equal the Laplace of x of t, and then minus 2 times the Laplace of y of t. Similarly for the second one, Laplace of y prime of t will equal 3, because we're going to use the linearity property, factor out those constants if we can. 3 times the Laplace of x of t, and then minus 4 times the Laplace of y of t. Okay, so now we use our transformations that we summarized here, and so I'll kind of like leave a little space and do it in pairs, like just keeping them lined up. So we'll have for the Laplace of x prime of t, s x of s minus lowercase x of 0 equaling the Laplace of x of t is uppercase x of s minus 2 times the Laplace of y of t uppercase y of s. And now for the second equation, the Laplace of y prime of t is s uppercase y of s minus y of 0, and that equals 3 times Laplace of x of t uppercase x of s, and then minus 4 times Laplace of y of t uppercase y of s. Okay, and what you want to do, just as we did before, is substitute the initial conditions now. So we have s uppercase x of s minus x of 0 was negative 1, so more efficiently plus 1, equaling x of s minus 2 y of s. And similarly, s y of s minus y of 0 was 2 will equal 3x of s minus 4y of s. Okay, now at this point we want to gather all of the terms that contain x of s and y of s on one side of the equation and everything else on the other side. And at the same time, let's do a little mental algebra. Okay, we're going to move this 1 to the right, and we're going to move this negative 2 to the right. But what I want to do is do some factorization at the same time and write the x of s and the y of s to the right of what's being factored. So for example, when I transpose this x of s to the left-hand side, at the same time I'm going to factor out the s and the minus 1 that would be obtained by the transposition. And I'm going to put that in front of the x of s. And then if we transpose this negative 2y of s, we just get plus 2y of s. And that's equal to the 1 here that's transposed, which gives us negative 1. So then at the same time, we'll do similar thing for y of s. First off, this 3x of s goes to the left, and that's the only x of s term. So minus 3x of s. But then for the y of s term, okay, we're going to have plus. We're going to factor out an s, and when we transpose this negative 4y of s, it becomes positive 4y of s. So therefore, factoring, we'd have s plus 4 times y of s. And that's going to equal this negative 2 that's transposed, which is a positive 2. And notice at that point that it's set up for Kramer's rule, because we've got the x of s's in one column and the y of s's in the second column. So we'll do the denominator off to the right here. And that would be the coefficients, s minus 1, negative 3, 2, and s plus 4. So that gives s minus 1 times s plus 4, and then minus a negative 6, so more efficiently, plus 6. And then at that point, we're going to want to manipulate this a little bit, FOIL this out. We get s squared, negative 1 plus 4 is plus 3s, minus 4, and then plus the 6, so s squared plus 3s plus 2, which actually factors as s plus 1 and s plus 2. So that's going to be our denominator. And that type of thing typically does happen, where after you calculate the determinant, you get an expression that you can then factor. Okay, so now for the numerator, we'll go for x first. So that's going to be replacing the x column by the solutions, negative 1 and 2. And then we leave the y's the same, 2 and s plus 4. So that's going to give us minus s minus 4 minus 4, or minus s minus 8. Okay, so what I'm going to do is I'm going to solve for x right away, and then we'll finish up, we'll find x, and then we'll do the same thing over again for y, in terms of calculating the numerator of y and such. Okay, so x of s then is going to be the numerator of x divided by the denominator. So it's minus s minus 8 over that factored form of s plus 1, s plus 2. But now you can see that Remember, we can't deal with products in the denominator. The only thing we can have is unique factors of linears or irreducible quadratics. So therefore, this is going to require partial fractions, just like we did in the IVP section. So set this up for partial fractions with two fractions, one with s plus 1 in the denominator, another with s plus 2 in the denominator. Since they're both linear, just constants, so a and b respectively. Working equation, minus s minus 8 equals a times bs plus 2, and then plus b times s plus 1. Because they're linear factors, we could use the elimination method. To get a, I'll let s equal negative 1. Then we have minus 1 minus 8 equals a times minus 1 plus 2. So then immediately we get 1 minus 8 is 7, negative 7, equals, looks like 1a, so negative 7 is a. And then if we let to solve for b, zero out its denominator, let s equal negative 2. And we get minus 2 minus 8 equals b times minus 2 plus 1. So then it's positive 2 minus 8 is minus 6 is negative b. And so therefore b is 6. Positive 6. Okay, so now x of s is in the partial fraction decomposition. A, which was negative 7, over s plus 1, plus b, which is 6, over s plus 2. And now for x of t. Okay, so that's lowercase x of t. And lowercase x of t is the inverse Laplace of x of s. So therefore, the inverse Laplace of what we just found. And so that would be using the linearity property, negative 7 times the inverse Laplace you can skip steps here if you like, of s plus 1 over s plus 1, and then plus 6, and the inverse Laplace of 1 over s plus 2. And so using our table, at this point that one should be familiar, the 1 over s minus a form, because e often pops up everywhere in differential equations. So 1 over s plus 1, a is negative 1, so we have negative 7 e to the negative 1t, or just e to the negative t, and then plus 6. And 1 over s plus 2, a is negative 2, so e to the negative 2t. Okay, so now that's the solution for x of t. We'll do it for y of t. So basically it's all this stuff here all over again. Try to squeeze it in. And so y, that's an uppercase y, is equal to, okay, the determinant. Leave the x's alone, so s minus 1, negative 3. Replace y by the solutions, negative 1 and 2. Let me put a little line here. Okay, so you know that's x of t. Now we got to do the same thing over for y of t. Okay, so we get 2s minus 2 minus 4. So 2s minus 6. And so that means that y of s is going to be n sub y over d. So that's the 2s minus 6 over the d was this s plus 1, s plus 2, recall. And it looks like more fun with partial fractions. So let me bring it up here because I don't want to try to not to run out of room. So we get 2s minus 6 over the s plus 1, s minus 2 equaling, okay, two fractions again, one with s plus 1, one with s minus 2. They're both linear, so therefore constants. And okay, I just noticed a mistake. 3 times 1 is 3, so that would be minus 3. Here, I'll color code it. That's the mistake which led to this mistake, so the 6's should be negative 5's. So I'm glad I caught that. Sorry about that. Thanks, Ryan, but I know you got that from your neighbor. So we get clearing the fractions to get the working equation. 2s minus 5 equals a times s plus 2. That should be a plus 2. Plus b times s plus 1. Okay, again, the elimination method. Solve for a, let s equal negative 1. So let me just do the arithmetic quick here. 2 times negative 1, negative 2, minus 5, minus 7 equals a. Alright, and let s equal negative 2 for b. And that'd be minus 2, minus 5, minus 9 equaling minus b. So b is positive 9. Okay, so now y of s by the partial fraction decomposition here, a negative 7 over s plus 1 plus b 9 over s plus 2. And finally, we could do the inverse Laplace for y of t. So y of t, the inverse Laplace of that result. And so, using the linearity property, y of t is negative 7, inverse Laplace, 1 over s plus 1, and then plus 9, inverse Laplace, 1 over s plus 2. And so finally, we get y of t. This is the 1 over s minus a again. So negative 7, s plus 1a is negative 1, so e to the negative 1t, or just e to the negative t. And then plus 9, 1 over s plus 2, a is negative 2, so e to the negative 2t. Okay, so that's the fun and excitement for systems. Got one more example That's even a little bit more exciting than that one, so come back in the next part and we'll solve that to finish off this topic.